this outline of my presentation. Now, let's begin with some research background. Solid oxide fuel cell convert chemical to electrical energy by phase challenge like high cost and material degradation, while proton ceramic fuel cell is operate at intermediate temperature but electrode can changes affecting the performance, while LSCF, our focus material, is widely used as cathode thanks to the mixed conductivity and the ORR activity. Moving on, here are the problem statements of my studies. First, conventional impedance analysis struggles to identify rate limiting steps due to overlapping process. Second, the RT analysis can separate them but it's not fully exploited. Third, thin film XRD reveals chemical states but its correlation with PRT remains unclear. So, as previous presentation focused on SOFC, PCFC, and LSCF, now this study also focusing on EIS and PRT. Electrochemical impedance spectroscopy (EIS) is a diagnostic tool by Nyquist plot merge overlapping process, while PRT transform EIS data into relaxation time, isolating charge transfer and diffusion, and also surface changes. Now, let's take a closer to the differences of CNLS and PRT. So, as you can see, complex nonlinear least square CNLS is a fitting method used for interpret EIS data through experimental spectra to an ECM. So it serves a complementary technique to the RT analysis to extract parameters such as polarization resistant RP and ohmic resistant RS. So in the conclusion, CNLS is overlapping process appear as merged semicircle, which is hard to separate. And lastly, CNS also limited in resolving hidden process. While compared to the RT, distribution of relaxation time, it shows how the RT provide clearer insight that Nyquist plot by resolving the individual electrochemical process, where it highlights that such peak correspond to a specific relaxation time which is directly tied to frequency range of high, medium, and low. So in the conclusion of DRT is transform EIS data into distribution of relaxation time. It separates overlapping semicircle of Nyquist plot and also quantifies contribution each mechanism process. This slide shows the workflow impedance of data analysis fuel cell for this research include Nyquist plot, DRT, and ECM. Next, there are three objectives. First is to relate the surface chemistry with electrokinetic. Second, to explore the ORR activity and polarization losses. Third, to determine the surface chemistry with electrode performance using DRT. Meanwhile, this slide shows the overall comparison flow of problem statement, objective, research questions, and the outcomes. Next, this shows the summarization of methodology that has been used in this study that cover the powder preparation, pelleting DCZ1 pellet, studies begin with the result of EIS from the Nyquist plot analysis to the DRT analysis. So the table on the right show the result of temperature 800 degrees Celsius and 750 degrees Celsius. They are the comparison of the area-specific resistant ASR from the Nyquist plot and DRT analysis. So the result of both analyses shows quite similar result. However, there is no similarity at 750 degrees Celsius. Next, this slide shows the differences of Nyquist plot and DRT of mechanism analysis at 800 temperature. So Nyquist plot, as you can see, is only plot 3 general frequency range of high frequency, medium frequency, and low frequency. Compared to DRT, DRT is more precise because it shows the mechanism process of each peak and quantify their contribution. So as you can see in the table, it shows every peak like P1, P2, P1A and P1B at high frequency is the bulk conduction in PCZY electrode, while peak P2A and P2 in the middle frequency show the charge transfer reaction of the electrode-electrolyte interface, and lastly, peak 3 at low frequency is oxygen diffusion and mass transport in LSF cathode. So at 800 degrees Celsius, DRT confirm proton conduction, charge transfer, and oxygen diffusion as distinct contribution. So making it a more powerful tool for mechanism and mechanistic analysis. Next, this is the part of surface chemistry of XRD LSF thin film. So in the pattern of XRD pattern, there are 3 main peaks have been highlighted in red box. So this presents the characteristic diffraction peaks of LSF perovskite space, where the first peak at 32.5145 peak angle is showed a strong intensity confirming good crystallinity of the thin film. Second, the peak at 46.7925 is correspond to the rhombohedral perovskite structure, where it's validating the stability of LSF at the atomic level. While lastly, the third peak at the 58.1151 is peak demonstrate of the coherent line, which indicate well-ordered lattice structure composed of lanthanum, strontium, cobalt, and iron atom. So together, this peak confirms that the successful synthesis of LSF perovskite phase and its sustainability for electrochemical application. In addition, the peak highlighted in the white box is actually considered as a defect signal because it doesn't correspond to the main perovskite structure, but instead arises from secondary phases with the thin film. So in the conclusion, this study ensured that the analysis focused only on the stable perovskite structure of LSF. So in the conclusion, the RT enabled precise identification of charge transfer, diffusion, and surface exchange mechanism. Next, LSF thin film show superior ORR activity, faster charge transfer kinetic, and minimize the polarization process. And lastly, XRD confirms structural stability with enhanced oxygen vacancy concentration, where it directly improving the ORR activity. Finally, for the future work, this study recommends extending the RT analysis, optimizing ORR activity, integrating XRD with EIS and or DRT, and lastly, conducting long-term stability testing. So I think that's all from me. Thank you for your attention and support.
Thank you very much. Okay, so ALIYA. Right, so now we will have the Q&A session. Can I see your slide from the beginning?
clearer, DRT has three range frequency. There are high frequency, low frequency, and middle frequency and low frequency. So any peak in a high frequency will be plotted here as LS and RS, which is as DCZY electrolyte. While middle frequency, for example at this peak, so it will recognize as first CPE, which has R1 and Q1, and third is at the low frequency will have Y own CPE at low frequency. So this picture is just example that I take from Google, not my actually result of graph.
Okay, next slide. Okay, so next. Okay, so in your method, okay, you prepare the both cathode and also the dielectric. Okay, so for the spin coating, so yang kuning tu apa?
Kuning this is the one.
This is ZY. ZY ke LCM? Tadi cakap LCM yang habis.
LSF bawah. Terus kita letak LCF.
Okay, biru LCM.
Betul. Biru tu sebenarnya LSF. Kuning tu DCZY, and then kita layering another LSF.
Okay, dalam thesis nanti mention tak spin coating berapa RPM? Did you mention that? Okay. Alright, for the EIF, okay, so you got the same result as the literature review, right? You get the 3R, right? Respective to the both, for the triple material, right? Okay.
But actually it's not 3 up. This is just the example.
Okay.
Goes,
Okay, move to the next. Your
so
result.
this is the exactly of my EP spot.
Okay, I have a question for this slide. Why did you choose only 750 and also 800?
Because I just take 2 of 4 temperature that I researched to just make a clearer that there 4 temperature has the same proportion, where it shows the as the temperature decrease, ASR increase.
What is the ASR?
Area specific resistance. So ASR I get from here. Okay, so this is the example of calculation how I get ASR, where the total peak value that we get, we total up and it is called RP. So the calculation is RP divided by 2 to get the value of ASR, and we compare of each temperature to get the best value.
Alright, so from the previous Google picture, right? So this is your result, right? Okay. So how you
P1B, P2A is actually shoulder peak. What is shoulder peak? Shoulder peak is not a sharp peak and unclear where it occur of two peak in a process, in a frequency range. As you can see in here, as you can see there are three. So this is not sharp and this is not sharp. So I label as a P1A, P1B, and also this P2A is the shoulder peak. So for the high frequency, they are plotted P1A, P1, P1A, P1B. At middle frequency, refer to the frequency range P2A and P2 inside the middle frequency, while P3 plotted in the low frequency. Same goes to the other DRT graph of other temperature. Because of for color is just I want to differences to show the difference, which is the brown color is show the high frequency of BCZY electrolyte, while the P2A